This is it. So in the last discussion, I said that this is the one. What was that? Down here. Use it as 2. We said that the magnitude of the induced current. Induced current is basically the current that is produced through the process of electromagnetic induction. Electromagnetic induction, like I said earlier on, it is the production of electricity using a magnet and a conductor. Even when they are not connected to some source, current can be produced by moving a conductor in a magnetic field or moving a magnet in a solenoid. It produces current. So the third point down here, this point here, the magnitude of induced EMF stands for electromotive force, which is basically the voltage or potential difference or the voltage, which is responsible for driving the current around in a circuit. And the direction of induced current can be determined by the application of the laws of electromagnetic induction. There are 2 laws that we're going to talk about in this session. Laws of electromagnetic induction. The first one, number 1, is Faraday's law, and the second law is called Lenz's law. So these are the 2 laws that we're going to talk about in this presentation. So the first law oops. Hey guys, I cannot see my screen.
They muted themselves.
This thing is freezing.
Mister, please hurry up.
Yes. Can you see the screen?
No.
Mister, I cannot see
Yeah.
the screen.
There's something,
No.
some kind of technical.
I mean,
Screen.
Yes.
Yeah.
What the hell was Hey, what's going on?
Can you allow me to?
Hey,
Wally, do it now.
control your
Yes.
children. Control your children.
Who's that? Wallace.
Come on.
Who's that?
Ayo.
Okay.
Ayo.
Shut up.
oi guys.
Take a shot. Take a shot.
Oi.
Oh, who's crying?
Okay.
So how? Control your children, guys.
Okay, guys. All right, that's good.
Yes, Mister.
All right, got the screen up again.
All good.
All right, and can you mute yourself, please?
Okay.
All right, here we go again.
Whatever.
Sorry, Mister.
Yeah, no, it's something that we have to cope with. So,
You can mute all.
all right. So laws of electromagnetic induction, two laws. We're going to, first of all, I got this objective here. We're going to name and state the two laws of electromagnetic induction. That's number one. Secondly, the second. Hey guys, can I ask you to mute yourself, please?
Leandra, please mute yourself. Courtney too.
I'm trying to get the screen. It's the same problem.
Mute yourself.
You wish.
Oh my god, who is that?
Guys, stop this. Can we actually have physics? This is the time.
Guys, what happened to Mr. Frel?
You're all a
I can't see the
The
screen, bro.
Can you see the screen?
Mr.
Mr. No.
No.
So there should be an
Only see
option
your
that
face.
says for you to share your screen.
We can see Courtney and Wallace's face.
Wallace and Courtney, I can only see you guys. And Jamal.
Who's that? Who's that
And
playing the
Katie.
music? Who's that playing the music?
Playing the music.
That's Manu. That's Manu.
Manu, useless.
Just naming everyone.
Oh, Mr. Come here. We are stuck here.
Not me.
Manu.
Oi, mute yourselves. Mute yourselves.
Shut your mouth.
I'm not. It's not me.
Faith on
I was playing the music, sir.
Faith Kondri.
Hey,
Wallace,
guys.
why do you keep changing your picture?
Yeah, who's arguing to you?
Jamal, are you playing music?
Guys, we're back. I mean, almost, I guess.
Mr. We can see the screen now.
Everyone, please mute yourself. Otherwise, we will mute you all. We are starting to listen.
All right, so I'm actually going to
Okay,
quickly
Mr.
run through the objectives again. You're naming and stating the two laws of electromagnetic induction. The second objective or the outcome is we're going to use the laws to identify the induced current direction. And finally, investigate the factors that affect the magnitude of induced current in a conductor and in a solenoid. So the two laws of electromagnetic inductions, the first one is Faraday's law. And Faraday's law, it states that the magnitude of the induced electromotive force or EMF is directly proportional to the magnetic flux linkage in a solenoid or the rate at which the conductor cuts through the magnetic field. So which means that the magnitude or the size of the induced electromotive force, which is basically the voltage to drive the current around the circuit, is directly proportional to the amount of magnetic field strength that is found inside the setting, and it is also direct proportion. It has a direct proportion with how fast the conductor is used to cut the magnetic field lines, and also how fast the magnet is moved in and out of a solenoid. The second point about the Faraday's law is that the induced electromotive force increases when the rate of change also increases. That means that the induced current is increased when a strong magnetic field is used, or two, the speed of relative motion is increased. So increasing the relative motion, it also increases the induced current. If induced current is increased, then it means that it requires a huge amount of induced electromotive force to drive that current around the circuit. So those are some of the things that we work together. Now, moving a little bit further down, we got Lenz's law. Now I got Lenz's law here. Lenz's law, it states that an induced electric current also flows in such a direction so as to oppose the change or motion causing it. Let's take a look at the diagram. There is a diagram that is given. Table given. Now when you take a look at this diagram here, we get a permanent magnet here, south pole on this end, and north pole out here. Once when the magnet is moved to the right, let's say the north pole is moved into this part of the coil, which is the solenoid. Once when this, let's say north pole is moved into the solenoid, what happens is that the law states that induced current always flows. Okay, the induced current will always flow in a direction so as to oppose the change or the motion causing it. What does that mean? It simply means that the north pole, the current will flow in such a way that it will oppose. Importantly, it will oppose the motion of the magnet. So once when the north pole is moved into this, it will move in this way, current will flow in such a direction that will try to oppose the movement of the magnet in the solenoid. What does that mean? It means that to identify the current direction, we're using right-hand grip rule. You're using right-hand grip rule. So using the right-hand grip rule, current directions are given. As you can see, current direction is moving up this way. Using the right-hand grip, we can identify that this is the north pole and that is the south pole. How do we do that? Using right-hand grip, north pole, south pole. You notice that the current flows in such a way to oppose this. When this becomes the north pole, using right-hand grip tool, we identify this as a north pole. Bringing in north pole, like poles, they repel, so it will push away this. So when this magnet moves away in the second setting, you notice that north pole is moved away, current direction, it changes again. So you notice that using right-hand grip, this time polarity changes. Current moving down this way, that becomes the north pole, this becomes the south pole. So we got a north pole and a south pole here. Opposite poles, they attract again. So it pulls in the magnet. So the magnet is going to move in and out. Once when that happens, current will continue to change its the direction. So when current changes its direction, that is basically fulfilling the Lenz's law. And that is the second law that we have. The same thing happens down here. That's north pole. South pole is brought closer to this solenoid. Nothing is connected. It's not connected to any source. It's just a galvanometer here. So what happens is when the magnet, the south end is moved closer, current moves in this direction. Using right-hand grip rule, we can identify that this is the north pole, this is the south pole. When this is brought closer, south pole, they're going to repel. It will push the magnet away. Once when it pushes the magnet away, again, current direction changes. current direction changes in it. Once when it moves up that way, using right hand grip rule again, this becomes North Pole, this becomes South Pole, and so you got a South Pole, North Pole, opposite poles, they're gonna attract each other. So again, it acts in such a way that it opposes the movement. The current flows in such a way to oppose the movement of the magnet, and that is Lenz's law. The application of Lenz's law and Faraday's law, we're gonna take a look at those in the next session. We lost much of our time in this the technical fault, so we'll talk more about